Titrations are a tool where you can take an acid or base, basically a solution that has a known concentration, and you slowly add it to an unknown solution where you're trying to determine that solution's concentration. So here what you'll do is you'll use a burette. So a burette is this long thin tube that has really accurate, precise measurements on the side, and you'll measure your initial amount, then you'll slowly add some of that solution into your unknown solution in a beaker below until you've reached the equivalence point. So the equivalence point is when your amount of acid equals your amount of base in your solution. So usually what we'll do is we'll use an indicator in here, and then it will change colors at ideally the point where we have our equivalence point. Titrations are a pretty cool technique because you can find out an unknown concentration of a solution just by doing color change and then using stoichiometry to find out the concentration eventually. First, we're going to talk about titration of a strong acid with a strong base. So just like before when we talked about strong acid and strong base, they are the easiest one because with a strong acid, we know that the exact concentration of my hydrogen ion is equal to the concentration of the acid, and my concentration of hydroxide is equal to my concentration of my metal hydroxide, because those are the only types of strong bases. So initially, if I have a strong acid, the concentration is going to, or the pH is going to be what the acid concentration is. And then you're going to be adding your base. So you'll see the pH slowly going up because as we add our base, we neutralize it. So we have hydrogen ion plus hydroxide going to water. So anytime we add some hydroxide, it's getting neutralized until we reach the equivalence point, and that's when all of our hydrogen ion is gone. And then it's going to rise very rapidly at that point. And so our equivalence point is going to be for strong acids and strong bases when the pH equals 7. That's when we have only water there. And so we're just have a neutral solution. Then if we keep adding base, then we're going to rise all the way back up to a more basic solution. And now we just have concentration of strong base. If I start out with a strong base, I'm going to start out at a high pH, and then I neutralize, so I now have my hydroxide solution. I'm going to add strong acid, which is hydrogen ion, and produce water. So as soon as I add any hydrogen, it gets neutralized, but I'm slowly losing my hydroxide until I've reached the equivalence point again. And once again, because I'm dealing with a strong base, my pH will be at 7 for the equivalence point. So you see this really big range where you just kind of drop pH. So big pH range, but a really short amount of volume. And then after I keep adding, then I now have an acidic solution, so I'm going to be at a low pH. So these ones are nice because they're pretty straightforward. So let's calculate the pH when I have 49 milliliters and 51 milliliters of a 0.1 molar sodium hydroxide solution when I have 50 milliliters of HCl. So if I was doing this titration, I have 50 milliliters down here of 0.1 molar HCl, which is exactly 0.1 molar of H plus ions. And in my burette here, I have my 0.1 molar hydroxide solution. So what we want to do first is figure out how many moles are in my hydrogen, or down here, so in my hydrogen solution, acidic solution. So I have 50 milliliters, and I'm going to convert that into liters, and then use a concentration 0.1 mole in a liter. So I have 5 times 10 to the negative third moles of hydrogen ion here. So after adding 49 milliliters, let's do A first. So for A, I have 49 milliliters of sodium hydroxide, which is my hydroxide. And so I need to get that into liters. And then I also have a 0.1 molar solution of that, so moles per liter. So I'll have 4.9 times 10 to the negative third moles of hydroxide. So if I think about an ice table, I'm going to do one over here. My reaction, let's think of it as a reaction table. I have hydrogen plus hydroxide going to water. And initially I have 5 times 10 to the negative third moles of hydrogen. And I have 4.9 times 10 to the negative third moles of hydroxide. So who is going to run out first? Well, hydroxide is my limiting reactant, so I'm going to get rid of all of that. I'll have 0. And so 4.9 times 10 to the negative third that. So I'll have 1 times 10 to the negative 4 moles of hydrogen left. So what I want to do is find out my pH. So I need to find hydrogen ion concentration here. And that's going to be my 1 times 10 to the negative 4 moles of hydrogen. But now my total volume I've added 49 milliliters plus 50 milliliters. So here I have 99 milliliters, which is equal to 0.099 liters. So my hydrogen ion concentration is 1.0 times 10 to the negative third molar. So then if I negative log that to get my pH, my pH is going to be 3. Okay. So now let's find out what happens when I've hit 51 milliliters. So we're going to have a very similar situation here. But now instead of 49 of hydroxide, I have 51. So once again, I'm going to have the same amount, same conversion, and what I'll end up getting is 5.1 times 10 to the negative third mole of hydroxide. So this is for B, so I'll make it red. So now in my ice table, let's do another one. I have the same amount of hydrogen ion because it's the same solution. But now I'm going to have a different amount of hydroxide. So I'll have 5.1 times 10 to the negative third moles. So now hydrogen is my limiting reactant. So I'm going to get rid of that. So I don't have any hydrogen left over. And now I have 1 times 10 to the negative 4 moles of hydroxide. So now I have a hydroxide solution concentration, and it's 1 times 10 to the negative 4 moles divided by my new total volume. So I have 50 milliliters from hydrogen, and then of my acid, and 51 milliliters of hydroxide. So that gives me 0.101 liters, or 101 milliliters. So that concentration ends up being, again, about 1 times 10 to the negative, 1.0 times 10 to the negative third molar. So then I can find my POH, which is a negative log of that value, which is 3.0. And so my pH is 14 minus that. And so that equals 11. So just adding 2 milliliters from that same solution, going from 49 to 51, I go from a pH of 3 to a pH of 11, and that's a really big change with just adding a few drops. So once we hit that equivalence point, which would be 50 milliliters of hydroxide, we have quite a large change in pH. So now let's talk about titrations of weak acids with strong bases, or technically also we could do the same thing with weak bases with strong acids. It'll be very similar, just reversed. So here, initially when I have a weak acid, that's just a weak acid solution. So I'm going to use the Ka of my acid to find the initial pH, right? Just a regular HA going to, in equilibrium with H plus and A minus. So don't forget everything we just learned. We'll do my little ice table, find out my concentration of hydrogen ion. Then, when we're in the buffer region, which is going to be this little region in here where I've partially neutralized my acid, so I have a good amount of conjugate base, I could use the Henderson-Hasselbalch. So yay, that is going to be where I have my negative, or my pH equals pKa plus the log of my A minus over HA. Okay, so that's in this region here. At equivalence point, my pH is going to be greater than 7. And this is because at equivalence point, if I have HA going plus a hydroxide, for example, creating, forward reaction only, water and conjugate base. So when I have equal amounts of this, I just have water and conjugate base. So because I just have a conjugate base, I'm going to have a basic solution. So here I'm going to use the pKb of my conjugate base to figure out my equivalence point pH. And then if I add more base, then I'm basically just going to have a strong base added at that point. So that's what it will be related to. If I have a strong acid with a weak base, similar process, but it will be flipped. So here is the process. First thing we're going to do is we're going to calculate the moles of weak acid that we have. Then we're going to calculate the moles of the strong base that we're adding. This is, and we're going to do kind of that reaction table here. We're going to see how much of my anion, my conjugate base, is formed, and then find out how much of my acid is left. Then I can use my Henderson-Hasselbalch to find the pH at the end. So similar to buffers. So let's practice. Let's calculate the pH when I have added 45 milliliters of a 0.1 molar sodium hydroxide to 50 milliliters of a 0.1 molar acetic acid solution. So I'm going to find out how many. So let's write the overall reaction first. So I have acetic acid, C2H3O2, the H up front, reacts with sodium hydroxide, which is going to react with the hydroxide. That's going to form water and then acetate. So initially, I want to find out how many moles of acetic acid I have. So I have 50 milliliters. I'm actually going to write it in a new place, sorry. 50 milliliters of acetic acid. I'm just going to call it HA. So I'm going to do 1,000 milliliters per liter, and then my concentration of 0.1 mole per liter. So I have 0.005 moles of acetic acid. So that's what I'm going to put here. 5 times 10 to the negative third moles. And then I'll do the same thing for this sodium hydroxide. So now I have 45 milliliters of sodium hydroxide. So 1,000 milliliters per liter and also 0.1 molar. So that gives me 4.5 times 10 to the negative third moles of hydroxide. So, and I don't have any of this. So here I'm going to have my change. Now hydroxide is my limiting reactant. So I'm going to get rid of it all. And that's how much acetate I'm going to create. So we do need to make sure for weak acids, bases, we need to create our conjugate because we don't just have water. So now for my conjugate base, or my acetic acid, I'm going to have 5 times 10 to the negative 4 moles. no hydroxide, and then I'll have 4.5 times 10 to the negative third moles. Okay, so now I can divide this by the total volume. So I have 45 milliliters plus 50 milliliters added together. So currently I have 95 milliliters, which is the same thing as 0.095 liters. So I'm going to divide both sides by 0.095 liters. So that's moles and over liters. And find my concentration. So my concentration of HA here is 5.3 times 10 to the negative third. Nope. Yep, that's right. And then over here I'll have 4.74 times 10 to the negative 2 molar of acetate. So that's my A minus. So now I could use my K expression here. So Ka equals products over reactants. A minus over HA. And I know my conjugate base and my acid amount. So I can find my hydrogen ion concentration. I'm going to multiply both sides by HA. So that goes away. And then I'll divide by A minus. And that goes away. So my hydrogen ion concentration is my acid over my conjugate base times by Ka. So that's going to equal, my acid was 5.3 times 10 to the negative third divided by 4.74 times 10 to the negative 2 times by my Ka, which is 1.8 times 10 to the negative fifth for acetic acid, and that gives me a value for hydrogen ion concentration equal to 2.0 times 10 to the negative 6 molar. So then I can take the negative log of this whole thing to get the pH. And then my pH equals 5.70. So since I haven't completely neutralized all of my acetic acid, it makes sense that I would still be a little acidic. So if I look at my strong acid over here, I'm at a very acidic solution up until I hit about equivalence point, and then I shoot up, and then I roll over here. As I start to have weak acids, pH of my solution really increases quite a bit as I get weaker and weaker. And you can see that my pH at equivalence point is a lot higher than for a strong acid. So as I have a weak acid, they have higher initial pHs than strong acids, which makes sense because they're not as strong. And then the pH change near the equivalence point is smaller. So for my strong acid, I had quite a large range when I hit my equivalence point for my pH. But for a weak acid, so let's look at this really weak acid, Ka of 10 to the negative 10, it just has a tiny little range at equivalence point. And that has to do with the buffering capacity. So I have this buffer region where my pH is pretty stable, and we also have quite a big increase initially of pH, and then it buffers out. And that means I don't have as much range to go when I hit equivalence. And then after the pH reaches the equivalence point, then I just really have strong base at that point. And then the pH for all of our weak acids is going to be greater than 7. So pH of strong acid will be 7. Everything that's weaker is going to be higher. So we can use indicators to help us know when we've hit our equivalence point. Indicators are weak acids, and they have a different color depending on if they have their acidic form or their basic form. So each indicator has its own pH range where it will change color. So we want to pick an indicator that's going to change color where our equivalence point is going to be, the pH of our equivalence point. This is called, so the point at which an indicator changes color, that's called the end point. So we want to find an indicator that has a similar equivalence point as our indicator's endpoint. So for example, methyl red has changes pH between somewhere between 4.2 and 6. So if I have an equivalence point up at pH of 9 for that acid, then my pH is gonna, or my indicator is gonna change colors way earlier than I've hit my endpoint. Here for phenolphthalein, it changes color between 8.3 and 10. So that would be a great indicator for this weak acid, because it will change color in my equivalence point range. So let's calculate the pH at the equivalence point for acetic acid, and then we'll do it for some other acids as well. So for acetic acid, we have 50 milliliters of acetic acid, so that's my known, with 0.1 molar of hydroxide. So let's write it out, the reaction. We have HA plus hydroxide goes to water and acetate. And I need to find the volume. Let's find out how many moles of acetic acid I have. So I have 50 milliliters, and I have 1,000 milliliters per liter, and then I have 0.1 moles of HA, acetic acid, per liter. Since I have a 1-to-1 ratio here, and based on my reaction, then for every 1 mole of HA, I have 1 mole of hydroxide, sodium hydroxide. So then I am going to find out the volume. So my concentration of sodium hydroxide is 0.1 mole per liter. And then I will convert the milliliters, 1 liter to 1,000 milliliters. So that gives me an amount that should say that it should take me 50 milliliters of sodium hydroxide. And if I stop right here, I can find out how many moles of acetic acid I have, and it's 5 times 10 to the negative third moles. So here I have, initially I'll have 5 times 10 to the negative third moles here. I'm also going to react all of it with my hydroxide, and I don't have any of my products. So at my change, I have 5 times 10 to the negative third for both. So I don't have any of my reactants left, and I only have my products, which is my water, which is not going to do too much, and then my acetate. So 5 times 10 to the negative third moles. So that's my amount. I'm gonna find the concentration by dividing by the volume. I mixed 50 milliliters of acid with 50 milliliters of hydroxide, so that gives me 100 milliliters of total solution, so I have 0.1 liters. So my concentration here is of acetate is 5 times 10 to the negative 2. Oops. Molar. So at equivalence, I only have acetate, which is a conjugate base. So I can find the Kb for acetate by doing my Kw over Ka for acetic acid. So that'll be 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5th. So my Kb here is 5.6 times 10 to the negative 10. Okay, so now we just have a weak base problem. I have my conjugate base, my acetate, sitting in water, which is literally what I have written right here, right? And now it's going to be in equilibrium and form a little bit of acetic acid and some hydroxide. It's going to basically just act like a base. So we have another equilibrium situation. So the amount of acetate I have is 5 times 10 to the negative 2. And I didn't have any acid or base. So now I'm going to have minus x on this side, plus x on this side, and we'll treat it like a regular old equilibrium problem. So now I have my Kb for my base, my acid, is equal to Ha times hydroxide divided by my conjugate base, or my base here. And that's going to be equal to x squared over 5.0 times 10 to the negative 2. And we don't need to worry about the minus x because Kb is really tiny. This whole thing is equal to 5.6 times 10 to the negative 10. So we can solve for x squared, and we end up getting, moving over here, sorry, x equals my hydroxide concentration, which is equal to 5.3 times 10 to the negative 6 molar. So if I negative log that to find the POH, I end up getting 5.28. So 14 minus that equals the pH, which equals 8.72. So many steps. Let's break it down. First step is to neutralize. Find out how much of your conjugate base you have left, and then find that concentration based on the total volume that you added. Then you're going to treat it like a weak base problem and find the OH concentration based off the Kb of your conjugate base, and then find the POH and then the pH. So many steps. I know it's annoying, but it's everything you've learned so far put into one large problem. So now I want you to try to do the exact same thing with two different other acids. Well, first, benzoic acid. So another weak acid, we have the Ka, and then try it with ammonia, which is a weak base. So I want you to pause. I'm going to wait like 20 seconds, and then I want you to try this on your own and see if you can get the answers. And then in about 20 seconds, the answers will pull up and I'll go over it. Okay, so let's talk about this fun one. So first thing we want to do is find out, well, a couple things. What is the equivalence point? So our amount of conjugate, or of our acid, benzoic acid, at equivalence is 1 times 10 to the negative 3rd mole. So I just found out how many moles are there of my acid. Then if you keep going and using the concentration of your sodium hydroxide here, you can find out what the volume of hydroxide is you need, and you're going to need that later. So we're going to have to add 20 milliliters of hydroxide to reach equivalence point. So we know at equivalence we have 1 times 10 to the negative 3rd moles of acid and therefore hydroxide. So that's what I have here, and I don't have any products. Then I'm going to react it all, and that's how much conjugate base I'm going to have. So then I know I have 1 times 10 to the negative 3rd moles of my conjugate base. I'm going to divide by my total volume now. So that's where that 60 milliliters comes in, which is 0.06 liters. So now I just have a weak base problem, and I have my conjugate base here, my benzoate, and I have a 1.67 times 10 to the negative 2 molar of that. So then I'm going to plug that into its own ice table. Now that's an ice table, not a reaction table. And I have a little bit of dissociation. I find my Kb for benzoate is Kw divided by the Ka of benzoic acid. So it ends up being 1.587 times 10 to the negative 10, so very weak. Plug it into a Kb expression, and we solve for x, which is equal to hydroxide, which tells us our concentration of hydroxide, solving for that x, is 1.63 times 10 to the negative 6. So to find the POH, I negative log that value, and I get 5.79. So to find the pH, I take 14 minus that. Okay, now we'll do the ammonia question, so feel free to pause. I'm going to pause again for about 20 seconds. You can then try it on your own, and we will reconvene. Okay, so let's figure this one out now. So we have ammonia, 0.1 molar of ammonia, and I have 40 milliliters of it, and I'm going to get to the equivalence point using 0.1 molar of hydrochloric acid. So once again, I'm going to find out the total volume of hydrochloric acid I'm going to need to titrate, and that's 40 milliliters, doing a bunch of stoichiometry. And I find out if I just stop right here that my equivalence point, my number of moles I have of ammonia is 4.0 times 10 to the negative third moles. So I can plug that into my reaction table, whoops, right there, and I find out that I have 4 times 10 to the negative third molar of ammonium, or moles of ammonium, and I'm going to divide by my total volume, which is 40 milliliters plus 40 milliliters, so 80 milliliters or 0.08 liters. So my concentration of ammonium is 5 times 10 to the negative 2 molar. So now I have a weak acid situation. So I'm going to write my my equilibrium equation for this. So I have ammonium dissociating into hydrogen ion and ammonia. I start out with 0.05 molar of it. I'm going to dissociate a little bit, and I create a little bit of my products. So I find my Ka, doing my Kw over Kb for ammonia, which gives me 5.6 times 10 to the negative 10 for my Ka. Plug into my Ka expression here, and solve for X. X is equal to my hydrogen ion concentration, which when we solve for X, we get 5.27 times 10 to the negative 6. Negative log it to get the pH, and that is 5.78 is the pH. And it makes sense that we have a weak base, so our pH at equivalent should be below 7, or if I had a strong base, it would be at 7. So that's a lot that we just did. One last thing is titrations of polyprotic acids. So when we have more than one proton available, when we do a titration, we're going to titrate one proton at a time. So there's going to be an equivalence point for each dissociation or each proton. I will not make you do one of these, but a cool thing is, and it doesn't even matter if you're doing polyprotic acids, we know that by using the Henderson-Hasselbalch equation, we can find that at this halfway point between our initial and our equivalence point, the pKa is equal to the pH at the halfway. So basically, okay, in general, if it takes 50 milliliters to get to the equivalence point, I'm going to go over to halfway of that, so 25 milliliters, and I'm going to go look up the pH at that point. So if I go over here, it's a little bit less than 1, maybe like 1.6. So then that's the pKa. So the pH equals the pKa, and that plus, right, the log of my A minus over HA. So at halfway, this is equal to 1, so log of 1 is 0. So halfway of equivalence, our pH equals pKa, which is really cool, and that's actually how we measure pKa values for our different acids. So once again, you don't need to do that for polyprotic acids. You could do it for any acid in general if I have, or base, if I have a weak base. And I'm going to start here, and I'm going to drop down, roll over. Here's my equivalence point. I'm going to find the halfway point, find the pH there, and that's going to be equal to the pKb. Well, for bases, it's actually going to be a little different, but the POH for that is going to be equal to the pKb. So, so cool. You can do that again for acid. So I can have my weak acid dissociating. So here's my equivalence point. right here. Halfway is about right here. So my pH at that point equals the pKa. Cool. So we'll do that in lab, and you'll get to calculate the pKa of a weak acid. So that should be pretty fun.